Okay. So first, we should know what are the non-parametric tests. As we discussed yesterday, the parametric test, they do have some assumptions regarding the form of the population or the, parent population, about the distribution of the parent population. But here non-parametric tests are which have no such assumptions, and if they are having some assumptions, so they are very, very poor. So let us discuss the non-parametric tests. So what do we do in parametric tests, and what are the parametric tests? So we know that a parametric statistical test is one that makes assumption about the parameters of the population distribution from which one's data are drawn. It means there we have one very crucial assumption that the parent population should be normally distributed. So here we do not consider any such type assumption that the population parent population should be normally distributed, from where we have to do the sampling, from where we have to take the sample. So a non-parametric test is one that makes no such assumptions. In this strict sense, non-parametric is essentially a null category, since virtually all statistical tests assume one thing or another about the properties of the source population. So I think someone is drawing here, someone is very fond of drawing, and the person is drawing very quickly. So please don't do that. If you have any query, any question, please ask us. We'll be happy to answer the questions, but don't do this one. You are just drawing the lines and arrows. So here we do not have any, rather we check if the parent population is non-normal, then we apply the non-parametric tests. So here it is also known as since non-parametric because we have no assumption regarding the form of the distribution of the parameters under consideration. That is why these are also known as the non-parametric tests. Sometimes we call them as distribution free test because we don't bother about the distribution of the parameter under consideration. So that is why sometimes we call them as distribution free tests. So now the question arises, because if we are dealing with the parametric test and the non-parametric test, so which one is more powerful? So obviously non-parametric statistical procedures are less powerful because they use less information in their calculation. For example, a parametric correlation uses information about the mean and deviation from the mean, while a non-parametric correlation will use only the ordinal position of pair of scores. It means in parametric test we use Karl-Pearson correlation coefficient, and in non-parametric we use Spearman rank correlation coefficient. So the difference between the two is that in Karl-Pearson correlation coefficient, we use the actual values of the two variables under consideration, while in Spearman rank correlation, we use only the ranks of the observations under consideration. So here the thing is that the difference, if there is huge difference between two observations, say one is 20 and another one is 80. But if there are no observations in between 20 and 80, so ranks will be given to next to 20. So that is why here we do not use the full information, original observations. So these are the less powerful tests in comparison to parametric tests. So whenever if we are in situation to get the assumptions of the parametric tests, then we go for the parametric test in comparison to non-parametric test. So if we have sufficiently large sample, then we go for the, so it approaches to normality and we use the parametric test there. Now these are the assumptions for the parametric tests, which are very crucial while performing the parametric test. The observations must be independent. The observations must be drawn from normally distributed population. It means the parent population should be normally distributed. These populations must have the same variance. We do talk about the equality of variance, whether I mean dealing with the two population, then we use the Levens test. Otherwise, we use the Motiloni's test for the equality of several variance. So these populations must have the same variance, and the means of these normal and homoscedastic population must be linear combinations of effects due to columns or homoscedastic means having equal variance. So that is this one is the assumption there. So normally distributed population and homoscedastic. Then we go for the parametric tests. Now counterpart of the parametric test are the non-parametric test, where we have no such assumptions. So certain assumptions are associated with the most non-parametric statistical tests, such as observation should be independent and continuous. It should be continuous as well. And lower order moments should exist, but these are fewer and weaker in comparison to the parametric tests. So here we have very weak, very few assumptions to perform the most of the non-parametric tests. The variable under consideration should be continuous, the observation should be independent, and lower order moments should exist. Now, what are the advantages of the non-parametric test? The probability statements obtained from most non-parametric statistics are exact probabilities. This is the advantage, not approximated. Regardless of the shape of the population distribution from which the random sample was drawn. It means we don't bother about the parent population, that whether it is normally distributed, not non-normally distributed, and if it is not non-normally distributed, then which distribution is followed by this population. We don't bother about that, and we calculate the probabilities for the events, and the probabilities are exact. And if the sample size are small, that is n equal to 6 or lesser, say, then there is no alternative to use the non-parametric test. It means if the sample size is 6 or lesser, then we apply the non-parametric test. And these are the easier to learn and apply than parametric tests, based on a model that specifies very general conditions, which we have discussed earlier. No specific form of the distribution from which the sample was drawn is required, and hence non-parametric tests are also known as the distribution, because we don't bother about the distribution of the parent population in normal distribution, which is non-parametric tests. So now, what are the equivalently, if we have some advantages, then on the other hand, we have some disadvantages as well. So these are the disadvantages of non-parametric test, that we lose the precision or wasteful of the data, because we are not using the data, we are just using the rank. So we are just wasting the data. Low power, these are not so powerful because we are using only ordinals or ranks of the data. False sense of security, we only feel that we have the security, that because we have just applied the rank, say 3 to 20 and the 4th to 80, but there is a huge gap between 20 and 80, but while there is equal gap in the rank 3 and 4. And testing distributions only, we can test only the distribution, which distribution is followed by the sample, or the sample is coming from which distribution. But we don't talk about the characteristics of that distribution. So higher order interactions are not dealt with, and parametric models are more efficient if data permit. It means if we have sufficient quantity of the data, then so that the assumptions of the parametric tests are met, then parametric tests are more powerful, more efficient than the non-parametric tests. It is difficult to compute by hand for large samples. If we have a large sample, then it is very hard to compute the value of the statistic of the non-parametric test. And tables are not widely available, but nowadays the things are available in different softwares. So in cases where a parametric test would be appropriate, non-parametric tests have less power, we know. So in other words, a larger sample size can be required to draw conclusion with the same degree of confidence by applying this, say, parametric tests. Now these are few points to be discussed. The inferences drawn from the tests based on the parametric tests such as T, F, chi-square and Z distributions may be seriously affected when the parent population is not normal. So whenever the population is not normal, we will not apply the parametric tests. We will apply only the non-parametric tests. The adverse effect could be more when sample size is small. If the parent population is not normal and we are applying that parametric test, the result will be badly biased, and it will very badly biased if the sample size is small. Thus, when there is doubt about the distribution of the parent population, a non-parametric method should be used. If you have any doubt that the parent population is normally distributed, then we should use the non-parametric test. But nowadays we can check very easily whether the population is following normal distribution or not. In many situations, particularly in social and behavioral sciences, observations are difficult or impossible to take on numerical scales, because we deal with the most of the cases in social sciences and behavioral sciences, we deal with the qualitative data. So a suitable non-parametric test is an alternative under such situation. So in such situations where we deal with the qualitative variable, say whether categorical variable, then we use the non-parametric test. This is a tree chart for the non-parametric test. You can see here that non-parametric test, then test of relationship between variables and test of difference between groups. Now here we can check chi-square test, Spearman rank correlation, binomial test, run test, and one sample Kolmogorov-Smirnov test. Now we come to two group and more than two groups. So here we deal with the independent groups and dependent groups, independent sample and dependent sample. So in the independent sample, we deal with the two variables and more than two variables. So in two variables, it means we are comparing the equality of, say, median or mean of two independent samples. So there we use the independent sample test, and here there are 4 tests to test the equality of median of two independent groups: Mann-Whitney U test, Kolmogorov-Smirnov Z test, Wald-Wolfowitz run test, and Moses extreme reactions. So among these, Mann-Whitney U test is more efficient. That is why it is very popular, and we use the Mann-Whitney U test as an alternative to the independent sample T test, to the parametric test, and it is the non-parametric. Now we come to more than two independent groups or variables. So in parametric test we use the ANOVA, one-way ANOVA, and here we use median test. It means here to test the equality of several medians, more than two medians, we use the median test, Kruskal-Wallis test, and John-Khire-Terpstra test. So among these, the Kruskal-Wallis test is very famous as it is very efficient. So we use the Kruskal-Wallis test as an alternative of the one-way ANOVA in parametric test. Now we come to the dependent samples. There for the two samples, two variables, we used in parametric test the pair t-test. So equivalent to pair t-test, the non-parametric tests are Wilcoxon signed rank test, the McNamara test, and the marginal homogeneity and sign test. So among these four non-parametric tests to test the equality of the median of the two dependent groups, this Wilcoxon signed rank test is very famous and it is very efficient. So we use Wilcoxon signed rank test as an alternative to the pair t-test in parametric test. Now we come to the more than two dependent samples. There we used repeated measure ANOVA and alternative to the repeated measure ANOVA, where the assumption of normality was not met for the population, parent population. So we used the Cochrane Q test, the Friedman test or Friedman ANOVA, and the Kendall's test. So among these three, the Friedman test or Friedman ANOVA is efficient. So we used this Friedman ANOVA or Friedman test as an alternative to the repeated measure ANOVA in parametric test.
Sir, why we always compare median?
Because in non-homogeneous data or say skewed data, which is non-normal, it is more robust in comparison to the mean. So mean is affected by the extreme observations and median is not affected by the extreme observations. That is why we use the equality of median. So it is as good as the mean for the non-homogeneous data set.
Okay, sir.
So, okay, now we come to one sample test, and that is binomial test, run test, one sample Kolmogorov-Swan test. So here the null hypothesis is proportion of two groups is same, that is 50%, 0.05 probability. Probability of success or say something else. And run test, it tests the whether the observations are random or not. So here the null hypothesis is that the observations are random. It means the observations are independent. The sample is independent. So observations in the sample are independent. Now we come to the one sample Kolmogorov-Swan test, that is case test. For one sample case test, the null hypothesis is that the sample comes from a particular distribution. So we can check whether the population is coming from say Poisson distribution, exponential distribution, so many theoretical distributions. Now we come to two independent sample tests. So there in parametric, we have discussed the independent sample t-test, and here we will be discussing the Mann-Whitney test. The non-parametric test for two independent samples are useful for determining whether or not the values of the particular variable differs between two groups. This is especially true when the assumption of the t-test are not met. And assumption, basically one assumption of the t-test, that is the parent population is normally distributed. So whenever the population is non-normal and we wish to compare the equality of say mean or median of two groups, then we apply this independent sample t-test, independent sample test, non-parametric test, and that is Mann-Whitney test. It is also known as Wilcoxon rank sum test. Wilcoxon rank sum test, and there we use for the dependent Wilcoxon signed rank test. This is not that one. This is Wilcoxon rank. So here the null hypothesis is that we may say that the median of the two here two. Now the two sample Kolmogorov-Swan test, the two samples have the same distribution, that is median. Wald-Wolfowitz run test, the two random samples come from the same population or they are having the same median. And Moses extreme observation, here also the null hypothesis is that extreme values are equally likely in both populations. It means the probability for the extreme observations in both the samples are same. Now here we will be discussing this through hands-on in SPSS, and suppose we have here the data to run the binomial test, one sample case test, and 2 sample independent sample test.
Sir, actually, like, what's the logic behind comparing the extreme values? Like, we always consider median, but here in this test,
Sometimes we are interested in sometimes we are interested in extreme observations. So this is the not very popular method, but sometimes we come to the situation where we are interested in, say, top 25% or 20% of the observations are extreme, say at the extreme end. So there we compare only the extreme observations there.
yeah, okay, sir.
So, Sama, can we take the questions after this session?
Yeah, definitely. It will be better if you note down the question.
Otherwise, we will not complete
at the last of the session.
Yes.
Yeah, yes, sir.
It will be better if you write down it. Okay. So here, see, we have genders, and these are the scores. So we have coded this categorical variable, and these are the scores. So male, 1 for male and 2 for female. So here we have 20 observations, and we will be performing these tests. So how to perform the, I mean, one sample carbon test or run test, or say this one, I mean, binomial distribution, check whether 50-50% of populations are there or not. So we will how to perform this in SPSS. So we will click on analyze, then non-parametric test, then legacy dialogues, then 2 independent sample, or say run test, and you can go for the whichever you wish. So suppose here we are using the two independent sample test. So we'll go to analyze, then non-parametric test, then legacy dialogues, and you can see here you can perform binomial run 1 sample case test as well. And you can apply the independent sample 2 test as well. So if you are applying this 2 independent sample tests, then this type of dialog box will be open there, and you have to put the test variable here, that is which is numerical variable, and the categorical variable will be put in this grouping variable, and you can go for the options as well. Otherwise you just tick which one you wish to perform the man-Whitney test and click on OK. So the result will be on the screen. So this way you can see here, that numerical variable is put here and the categorical here, and you have to define the group, 1 for male and 2 for female. So you have to write 1 and 2. So this way you write 1 and 2 for the 2 groups, and in option you can click on descriptive, quantiles, and the 2 things, and you click on continue and then click on OK. Then you will get the output of the these tests, that is man-Whitney test. So the descriptive statistics is here, that this is not actually example which we have. This will be performed in hands-on, and here we have taken another example. So here say 40% are taken for the cholesterol concentration, and their mean cholesterol is this, standard deviation is this, maximum minimum is these, and here you can see the different percentiles, 25%, 50%, this is median, and the 75%. And since this is not very informative, since this is here we have used only the codes 1, 2, 1, 2 for the male and female, so we'll lift it. It is not informative. Now the rank table, here we can see the rank table. So you can see the ranks. So you can see the rank, cholesterol concentration with the 2%, the 40% having the problem of cholesterol are put on 2 say processes. One is diet and another one is exercise. So 20% are on special diet and 20% are on exercise. and so their mean ranks are 25 and 16, and the rank sum is 500 and 320. So you can see now this is the Mann-Whitney U test, and here we can see the p-value is less than 0.05. So it means there is a difference between the two groups. It means diet and exercises are having the impact on reducing the cholesterol level, say, and they are not equal actually. They are different in nature. And from the mean score or mean ranks or some ranks, we can see that which one is going to be more effective. Now test for two related samples. Related samples means we are using the alternative to the pair t-test. Here we use Wilcoxon signed rank test, McNamara test, marginal homogeneity, and sign test. See, there are some slight differences in the different tests. So as per the situation, we use that test. So the non-parametric test for two related samples allow you to test the differences between paired scores when you cannot or would rather not make the assumption required by the paired sample t-test. So here in paired sample t-test, we assume that the requirement is there to that the parent population should be normally distributed, but here this assumption is not required, and we get the scores of the differences of the two variables, and the procedures are available for testing normal, ordinal, nominal, ordinal, or scale variables. It means here we are dealing with the categorical data, categorical variable. And this is so for this we use the Wilcoxon signed rank test, a non-parametric alternative to the paired sample t-test. The only assumption made by the Wilcoxon signed rank test are that the test variable is continuous, and it is for all the non-parametric tests, and that the distribution of the difference scores is reasonably symmetric. It is just close to the normality, but not normal, but it should have the shape almost symmetric. Then we apply this Wilcoxon signed rank test and McNamara method test the null hypothesis that binary responses are unchanged. As with the Wilcoxon test, the data may be from a single sample measured twice or from two matched samples. Maybe related samples, or you just apply two times the sampling. The McNamara test is particularly appropriate with the nominal or ordinal test variable for binary data. It means if we are having only two categories of the data, male, female, present, absent, yes, no. So there we apply McNamara. Unlike the Wilcoxon test, the McNamara test is designed for use with nominal or ordinal test variables. Now, marginal homogeneity, if the variables are multinomial, more than two categories. If they have more than two levels, then we use the marginal homogeneity, and otherwise McNamara. And for all these, we can use this, Wilcoxon signed rank test. And sign test is also used for testing the equality of median of two samples. Wilcoxon and sign are used to continuous data, and of the two, Wilcoxon is more powerful. That is why it is more famous, and we use the Wilcoxon signed rank test. Now, suppose here we have some data of the persons, say cancer patients. This is their ages, and these are their stages, and these are the survival of the patients, 0 week, 2 week, 4 week, and 6 week, and these are the observations. So this way we can use the repeated measure. So Wilcoxon signed rank test using SPSS. How to apply this one? So the Wilcoxon signed rank test is the non-parametric test equivalent to the independent t-test. Not it is equivalent to the pair t-test. As the Wilcoxon signed rank test does not assume normality in the data, it can be used when this assumption has been violated and the use of the dependent test t-test is inappropriate. Here we use the dependent, actually it is written to the dependent t-test, and dependent t-test is that nothing but it is pair t-test for the two samples. So it is used to compare two sets of scores that come from the same participants. We have repeated the observations. So this can occur when we wish to investigate any changes in scores from one time point to another, or when individuals are subjected to more than one condition, as we do in case of second suppressant. Or you are using some technique to reduce the weight. So we have taken the weights of the persons, same persons, say in first month, second month, third month. So this way we will use the Wilcoxon signed rank test, which is an equivalent non-parametric test to the pair t-test. So these are some assumptions as we have discussed for the parametric test as well. So there are some assumptions for the non-parametric test, and these should be the variable should be continuous, the observation should be independent, and the lower order movement should exist. So these are such type of assumptions, very weak assumptions are required for the non-parametric test. So let us see which are these assumptions. So these three assumptions are briefly explained below. Assumption 1, your independent variable should be measured at the ordinal or continuous level. Assumption 2, your independent variable should consist of two categorical related groups or matched pairs. And the assumption 3 is that the distribution of the differences between the two related groups, that is the distribution of the differences, not of the observations. We take the difference of the observations taken twice, and we are talking about the distribution of that difference between the scores of both the groups of the independent variable. For example, the reaction time in a room with blue light and a room with red lighting needs to be symmetrical in shape. It means the difference of the scores of the observations taken twice on a sample should follow a symmetric distribution. It should be a symmetric shape. So how to perform this dependent sample test, non-parametric test in SPSS? We just click on analyze, then go to the non-parametric test, and then go to legacy dialogues, and there you will see two related samples, and click on that. So this dialog box will be opened. You just put one variable here, another variable here, and you just click on the Wilcoxon signed rank test, and you can go for the option as well and click on OK. Then you will get the analysis. So this is descriptive. Here we have taken 25% say of cancer patients. So these are the score are the levels of pain before say chemotherapy and after chemotherapy. So these are their scores: percentile, decile, minimum, maximum, standard deviation, and mean. Now we calculate the ranks. So here we say that the negative ranks are 11 and positive ranks are 4. Mean rank are 8 and 8, and some ranks are 88 and 32 for the pain score post and pain score pre the test. And ties, there are ties. It means the difference will be 0. There are 10 ties there in the data, and total are 25. So here we have alternative hypothesis that pain score post is less than pain score pre, pain score post is greater than pain score pre, pain score post is equal to pain score. Now, this is the test statistic table. Test statistic table, by examining the final test statistic table, we can discover whether these changes due to the acupuncture treatment, say acupuncture we have used, led overall to the satisfactory, statistically significant difference in pain score. We have used the actually acupuncture technique. So the pain level before acupuncture and the pain level after acupuncture. So we are looking for the asymptotic significant value, which is in this case, it's which is for this case 0.071, which is more than 0.05. This is the p value for the test, and we report the Wilcoxon sign rank test using the Z statistic, that is this one. And here the value of the Z statistic is this, and the p value is 0.071, which is more than 0.05. So here we assume that the pain level before and after acupuncture are same. Reporting the output from the Wilcoxon sign rank test. A Wilcoxon sign rank test showed that a 4-week, twice weekly acupuncture treatment course did not elicit a statistically significant change in the lower back pain in individuals with existing lower back pain. So indeed, median pain score was 5 both pre and post treatment, because here we are using the equality of median of the two scores before and after the acupuncture technique. Now we come to the K independent sample test. So in this is the test equivalent to the one-way ANOVA. So non-parametric test for multiple independent sample are useful for determining whether or not the values of a particular variable differ between two or more groups. It means we are just checking whether the equality of median for all the groups. This is especially true when the assumption of ANOVA are not met, and in ANOVA we first check whether the parent population is normally distributed or not, and there is equality of variances or not. So these are the assumptions for the ANOVA, and when these assumptions are not met, we use the corresponding non-parametric test, and that is Kruskal-Wallis test. So here we use median test, Kruskal-Wallis test, and John-Khire-Terpstra test. So let us see in the situations for these tests and null hypothesis for these tests. So the null hypothesis for the median test is that 2 or more independent samples have the same median. All medians are equal. It assumes nothing about the distribution of the test variable, making it a good choice when you suspect that the distribution varies by group. If you are having any doubt that all the groups are having different distribution, then we should go for the median test. Now multiple independent samples come from the same population, that is all medians are equal. Non-parametric analog to the one-way ANOVA. So this is one-way analysis of variance by ranks, that is for the categorical variable. Now John-Khire-Terpstra test also tests the equality of median of the several groups. Now suppose here we have some data. We have a type test, and these are the score of type test, time taken in the type test. And there are 3 groups: beginners, intermediate stage participants, and advanced learning stage participants. So we have coded 1, 2, 3 for beginners, intermediate, and advanced. So now how to perform this in SPSS, Kruskal-Wallis test. The Kruskal-Wallis test, sometimes also called the one-way ANOVA on ranks, is a rank-based non-parametric test that can be used to determine if there are statistically significant differences between 2 or more groups. 2 groups may also be checked, what we have done in Mann-Whitney U test. So here we can use, so Mann-Whitney U test will be a particular case of this Kruskal-Wallis test. So it is considered the non-parametric alternative to the one-way ANOVA and an extension of the Mann-Whitney U test to allow the comparison of more than two independent groups. So similar assumptions are here for the Kruskal-Wallis test. Let us see. Independent variables should be measured at the ordinal or continuous level. And assumption 2 is that your independent variable should consist of two or more category independent groups. Typically, a Kruskal-Wallis test is used when you have three or more categories, categorical observation, independent groups. But it can be used for just two groups. That is Mann-Whitney U test, because this is particular case of this one Kruskal-Wallis test. So third assumption is that you should have independence of observations, which means that there is no relationship between the observations in the group, in each group, among the group, between the group. And okay, so fourth assumption is in order to know how to interpret the result from Kruskal-Wallis test, you have to determine whether the distributions in each group, that is the distribution of scores for each group of the independent variable, have the same shape, with also means the same variability. Same shape means we are talking about the variability, that is as we applied their Motley's test. So here we talk about the sphericity of the variance. Now to perform this in SPSS, we just click on analyze, then go to non-parametric test, then go to legacy dialogues, and again we go for the K independent sample test. So this way the dialog box will be open. You have to put the dependent variable here and categorical here, grouping variable here. So penny score, and this is drug treatment group. So you just put here and then click. And the define, you have to define the range here, because if you are dealing with the 3 groups, we're dealing with the 5 groups, so you have to define the range 1 to 5, 1 to 3, this way. And you just click on the Kruskal-Wallis test and then click OK. After defining the group, and you can go for the options also. So this way we are dealing with the 3 groups, so 1 and 3. And then click on continue and then click. Go to the option, then you can put on tick on descriptive and quartiles. Otherwise, you just click continue and then click on OK. So this Kruskal-Wallis test will be opened here. This is the table for the ranks. So we have used 3 drugs, drug A, drug B, drug C, and these are the pain scores of 20 persons, and these are their mean ranks. So from here you can have idea which one is going to be significant. So these 2 are non-significant, but third one is significant to both A and B. So okay, so here we can see the value of the chi-square is 8.5 and degree of freedom is 3, since we are using 3 groups only. So n-1, that is 3 minus 1, 2 degree of freedom, and the p-value is 0.014. It means here the p-value is less than 0.05. So it means the drugs are effective. The drugs are not having the mean score or median score as seen. They have different impact on the on reducing the pain. So reporting is that we see the p-value, and on the basis of the p-value we reject or not reject the null hypothesis. Now, how to perform the Friedman test, or say equivalent to the repeated measure ANOVA in SPSS? The Friedman test is a non-parametric alternative to the one-way ANOVA with repeated measures. It is used to test the differences between groups when the dependent variable being measured in ordinal scale, where rank matters. So it can also be used for continuous data that has violated the assumption necessary for the one-way ANOVA test. So here we use the repeated. This is an alternative to the repeated measure ANOVA. as we do. So then when non-normality will be there, so there we will apply this non-parametric equivalent to the repeated measure ANOVA, that is Friedman ANOVA or Friedman test. The assumptions are same, almost same as we use in non-parametric test. So let us see. When you choose to analyze your data using a Friedman test, part of the process involves checking to make sure that the data you want to analyze can actually be analyzed using the Friedman test. It means the assumptions should be met. So you need to do this because it is only appropriate to use a Friedman test if your data passes the following 4 assumptions. The one group that is measured on 3 or more different occasions, that is, we have taken the repeated measure, repeated observations more than twice. The group is a random sample from the population. The observations are independent, taken from the population. Your dependent variable should be measured at the ordinal or continuous level. And the sample do not need to be normally distributed. It is very important and crucial assumption to perform the non-parametric. So the Friedman test procedure in SPSS statistics will not test any of the assumptions that are required to test this, because it directly gives the results. So we have to make sure that the assumptions of non-parametric tests are met before performing the non-parametric test in SPSS. So in most cases, this is because the assumptions are a methodological or study design issue. That is why they had not been given in SPSS to check the assumptions, and not what SPSS statistics is designed for. And this statistics is not designed for testing whether the assumptions are met or not. It is designed to test the perform the test only. So in the case of assessing the type of variable you are using, SPSS statistics will not provide you with any error if you incorrectly label your variable as nominal. So you have to use their categorical. So if you are using nominal, not ordinal, so it will show no error. Now we use an example to illustrate this Friedman ANOVA in SPSS. So a researcher wants to examine whether music has an impact on the perceived psychological effort required to perform an exercise session. The dependent variable is perceived effort to perform exercise, and the independent variable is music type. So which consists of 3 groups: no music, classical music, and dance music. So to test whether music has an effect on the perceived psychological effort required for performing an exercise session, the researcher recruited 12 runners who each ran 3 times on the treadmill for 30 minutes. For consistency, the treadmill speed was the same for all 3 trials. So in a random order, each subject ran listening to the no music at all, listening to the classical music, and listening to the dance music. At the end of each run is 3 runs for all 3 different type of musics. Subjects were asked to record how hard the running session felt on the scale of 1 to 10. 10-point Likert scale it was asked. How many score you will give for say listening with no music, with classical music, and with dance music in 10-point score out of 10. So with 1 being easy and 10 extremely hard, a Friedman test was then carried out to see if there were differences in the perceived efforts based on music type: no music, classical music, and the dance music. So here we have say scores with no music, classical music, and dance music. So you have to perform the Friedman test. So how to perform it in SPSS? We go to analyze, then click on non-parametric test, then go to legacy dialogues, and then go to K related samples, because we are using the repeated observations more than twice. So here we have all three type of scores. You just put them in test variable, go to statistics and click on the Friedman ANOVA and click on OK. So you will have the output. Statistics, you can have descriptive statistics, quantiles. So you put which you wish and then click on OK. So you will get the descriptive statistics. Here we have 12 persons. There is these are the percentile of their scores, and these are the ranks with the no music, classical music and dance music. So you can see here which one is going to be significant. 2.3 is very close, 2.1 is close to 2.3, but 1.4 is not close to this one. So this is going to be significant dance music in perceived performance. So here we can see that the p-value is less than 0.05 as it is 0.022. So there is a significant difference, and the difference is due to this dance music. Now, when the null hypothesis is rejected, then we go for the postdoc test and we check which pair of treatment is going to be significant for the rejection. So here we can see from the mean score that this is going to be significant with both A and B. You can see here classical, dance, and this is classical with none, this is dance with none, and dance with classical. So here you can see p-value is very high, p-value is very low, and p-value is high. So dance and classical are non-significant. They are equivalent to each other. Classical and non-music are equivalent to each other, but dance and non-music are significant because the p-value is less than 0.05. So how to report? We report the data on the basis of the p-value and also on the basis of the p-value for the postdoc test as well. So now how to perform the chi-square test to the data? So chi-square test is used when we compare the two categorical variables at a time. So here we check the independence of the attributes. So when we are dealing with the two attributes. So chi-square test for independence, also called Pearson's chi-square test or the chi-square test of association of attributes, is used to discover if there is a relationship between two categorical variables. So these are some assumptions and very close to the previous assumptions to perform the chi-square test, as we are using it as the non-parametric test, but this test is the test which is parametric at the same time, and it is non-parametric. So assumption 1, the two variables should be measured on the ordinal or nominal level, that is categorical data. You can learn more about, we know ordinal and nominal variable. And the assumption 2, your two variables should consist of two or more categorical independent groups. Example, independent variables that meet this criteria include gender, say group male, female, and this way, and ethnicity, that is groups Caucasian and African American, and this way. So physical activity level, that is 4 groups, say sedentary, low, moderate, and high. And professional, you can have say group 5 groups: surgeon, doctor, nurse, dentist, therapist, and so on. So how to perform this chi-square test in SPSS? We go to analyze, then descriptive statistics, and there you will see the cross tab. So you click on that and you will see the row and column. So you put one attribute here, another attribute here, and you can go for the statistics. And here one assumption for the chi-square test is that the cell frequency should not be less than 5 because continuity is break there. And if it is less than that, then we pool the all frequencies less than 5 to maintain the continuity of the distribution. And then you can have the bar chart of the display clusters and suppress table, and just click on OK. Then we will get the output. So here we have to put on this chi-square. You can have different counts. Okay, this way the independence of attributes will be checked. So this way you can see the gender and preferred learning medium cross tabulation. Male, female, male with the books, male with online, female with the books, female with the online, and the total. You can say how many percentage. So 16 out of 40 male study book through books and 24 online. So 40% rely on books and 60% on they study through books. And so you can see here 13, 27. It means 25, 32% and 67%. And the total overall 29 and 51. So 36% are studying through books and 63% or 64% through online. Now this is the chi-square test. You can see here the p-value for all the different type of Pearson chi-square, continuity correction, likelihood ratio, Fisher's exact test, and so on. You can see here all are non-significant. It means the attributes are, the two attributes are independent to each other. They are not associated with each other because the p-values through all tests are coming to be more than 0.05. So this tells us that there is no statistically significant association between gender and preferred learning medium. That is, both male and female equally prefer online and learning versus books. So this way you can see Kramer's V as well, and these are also non-significant. So this data we will be using for performing this test in say SPSS. So this was all about today's discussion about non-parametric test. Okay, so we have some case studies. Say first one is with the Mann-Whitney U test. So we have a case study of say depression. A psychiatrist might collect data to investigate the depression effects of certain recreational drugs. He tested 30 clubbers in all. 15 were given tablet to take on a Monday night, and 15 were allowed to drink syrup. Level of depression were measured using the tested scale the day after Tuesday and Friday. Okay. It is taking little bit time. Okay. So, okay. So here we have data for the two, say, data on the depression level on Tuesday and Friday. So here to perform this non-parametric test, we should click on analyze. So okay, let us see this. So here we have given code 1 for the tablet and 2 for the syrup. So now to perform the analysis non-parametric test, we go for the non-parametric test, go to legacy dialogues, and you can go here for to perform say one sample t-test, one sample Kolmogorov-Swann test to check which distribution it follows. So we check for say both two variables, or you can have for only one variable, and you can check uniform, exponential, Poisson, normal, all you can check, and you can also have some descriptive statistics and then click on OK. So this way you can have a test. And on the basis of the p-value, this you can see whether it is having a particular distribution or not. So thus this one sample Kolmogorov test, this has been applied for the normal distribution. And you can see here on the basis of the p-value, it is very much less than 0.05. So it is not following normal distribution. It is not even following the uniform distribution because p-value is very less than 0.05. It is following the Poisson distribution as the value is p-value is more than 0.05 and very high. And here it is also not following the exponential issue. So the data is coming from the Poisson distribution. Now we can perform these two for both. So you can see, click on analyze, go to non-parametric and go to legacy dialogues, and you can also check the binomial distribution. So you can see here the test variable is this, and you can go for the options. So descriptive, okay, and then no need of it. We test 50-50% for syrup and I mean that, and you click on OK. You can see here. There are more than 2 values for Tuesday. Binomial test cannot be performed. So there must be one observation only with 50-50% we check. So here this is not the case. Now we can apply another non-parametric test, say run test. We can check whether the observations are independent or not. So median will be okay. Okay. So descriptive, okay. The p-value is rejected. The p-value is very much less. P-value is 1. It means the observations are independent. Sorry. Now we come to the another non-parametric test, and that is man-Whitney U test. So we click on non-parametric test, click on analyze, then go to non-parametric test, then go to legacy dialogues, and we go to 2 independent sample test. Okay, so test variable will be put here because this is the case of repeated observation. We have twice taken the observation. So here we are taking this one, and grouping variable is drug type. We have to define group 1 for tablet and 2 for syrup. Okay, continue and go for the option if you wish descriptive statistics, and then man-Whitney U test and click on OK. So here you can see here 30% are taken. Number is 30, and we have taken observation on Tuesday, and the mean score is 18.43. Standard deviation is this, minimum is 13 and maximum is 35. Now you can see the ranks for the tablet and syrup. The rank 15% are for the syrup and tablet, and the rank mean rank is 17 for the tablet and 13 for the syrup. So you can see the difference. So it is going to be, I think, significant or not, we will see. And these are the rank sum. Now we come to the statistic, and you see here the p-value is 0.2. 0.203, which is more than 0.05. So for this example, the tablet and the syrup are either equally effective or they are not effective, because the null hypothesis is accepted that both are equally effective or both are not effective. Okay. Now we come to for the repeated measure ANOVA, repeated samples for the two group which we have taken here. So we go to legacy dialogues and go to say two related samples. So one will be here, another will be here, and you go for the Wilcoxon sign rank test and go for the option and click OK, then click OK. So this way you can see this is going to be non-significant. So as we have taken in the case of that one, PU test, it is also going to be non-significant for twice on the Friday and on the Tuesday. So here we can see the p-value is more than 0.05 because it is 0.13, which is more than 0.05. So for both the observations, it is going to be non-significant. It means tablet and both are either equally efficient, equally effective for both the week days, Tuesday and Friday, or both are not effective for the two observations. Okay. Now we come to the case of another example. Say we have taken different statistical tests we have applied for the same data, but we have also for different. We have different data for different cases. So here we have the Wilcoxon signed rank test. So a retailer wants to know the impact of print advertisement on sale. He used print advertisement for 1 month period to his 10 outlets. He observed sale results before experiment and after experiment. So this is the case of also Wilcoxon signed rank test, that is repeated measure type. This case. So let us see this one. Okay, so before and after, so we'll go to analyze, then non-parametric test, then go to legacy dialogues and go to two related samples. One is here, another one is here, and so this one you can see this is not going to be effective here also, because the p-value is very high. P-value is high. It means the advertisement is not going to be effective. Okay. Now let us consider another case study for the say Kruskal-Wallis test. So here we have a case study. Scientist has discovered that the caffeine consumption linked to higher heart rate. Researcher took 40 participants and split them into 4 groups that varied in a number of caffeine consumption. The first group was a control group and had no coffee at all per day, that is none in the whole month. The second group had 1 cup coffee per day. The third group had 2 cup coffee per day, and the final group had 4 cup coffee per day. At the end of the month, all of the participants were measured heart rate score. And let us see Kruskal-Wallis test. means equality of median of more than two groups. So here you can see here we have coded 1 for no coffee, 2 for 1 coffee, 3 for 2 coffee, and 4 for 4 coffee per day. So now we go to analyze, then non-parametric test, and go to legacy dialogues and go for the K independent sample test. Okay, heart rate score is dependent variable and coffee consumption group, and here we have minimum 1 and maximum 4. Continue, go to option, descriptive, click Kruskal Wallis test. Okay. So here you can see here 40 persons are there. These are their mean scores, and here you can see their ranks. No coffee 10%, 1 coffee 10%, 2 coffee 10%, and 4 coffees 10%, 40, 10%. And these are their mean scores for the heart rate. Now you can see here the p-value is 0.006, which is very much less than 0.05. So it means the coffee consumption is effective further heart rate. It impacts the heart rate because the null hypothesis is rejected here. And we can see here also the no coffee, the person with no coffee, the average mean score is 16. With 1 coffee it is 19, but with 2 coffee it is 14. It is reduced here, but 4 coffee it is 31. So you can see here the differences. That is why it has been rejected. Now we come to repeated measure ANOVA. That is here we use the Friedman ANOVA. So here we use the marketing campaigning. To test the marketing campaign, the researcher took 15 retail outlets who considered being in need of increasing sale and putting them on this campaign for 2 months or say 3 months. Their sales were measured in millions at the start of the campaign and then after 1 month and 2 months. So we have 3 observations here. Friedman ANOVA. Okay, so these are the sales in millions at the start of the campaign and after 1 month and after 2 months. Let us see whether this advertisement is going to be effective or not in increasing the sale. So we go to analyze, then go to non-parametric test and legacy dialogues, and then go for the K related samples. Select all and put them here. Go to the statistics. You can have descriptive statistics, you can have quartiles as well, and again go to Friedman ANOVA and click OK. So here you can see the descriptive statistics, mean, standard deviation, minimum, maximum, and these the 3 percentiles, 25th, 50th, and 75th percentile. So you can see here all the 3 scores, 15, 15, 15, same retails are taken into consideration at the start of the campaign, after 1 month campaign, after 2 month campaign. So you can see here the mean score is 82, 81, and 80, almost similar to each other. So now the mean scores are 2, 1.8, and 2.1. These are also similar. So you can see here the p-value is 0.766, which is very high than 0.05. So in this case, we can say that the advertisement is not going to be effective, and because the scores equality of all the average score or median sale is same for all the 3 data taken at the start of the campaign after 1 month campaign, after 2 months. So campaigning is not going to be effective in increasing the sale. Okay, now come to chi-square test. So here we have a case study, chi-square test. So where is the data? Let us come to the final data. Yeah, here we will be applying the, here we have the data of education level of the persons, male and female. So here you can see we have the data, we have coded 1 for male and 2 for female, and we have the type of gender is it is having 2 category, male and female, and the education is having 4 category, high school, intermediate, UG and PG. So we have given code 1 for high school and 2 for intermediate, 3 for UG and 4 for PG. So now we will see whether gender is independent of education or education is independent of gender or not. Okay, so here you can see here that gender is given, we have coded 1 for male and 2 for female. You can see here 2 for female, and we have coded 1 for high school, 2 for intermediate, 3 for UG and 4 for PG. Okay. So now we perform the chi-square test. So we go to analyze, then descriptive statistics, and go for the cross type. So you have to serial has no meaning. You put one variable here and the variable here and go for the statistic chi-square test, and you can have also phi and Kramer V and something else if you wish. Click on OK, and I don't think anything else is needed. So you can have a cluster chart and then click OK. You can see here 60% are taken into consideration and none one is missing. And you can see here gender of subject versus education of the subject cross tabulation. So you can see here there are 7 male with high schools, 6 male with intermediate, 8 male with UG and 9 male with PG. So total 30 males are there and 30 females are there, which out of 38 are high school, 6 are intermediate, and 9 are UG and 7 are PG. Now this is the chi-square test. You can see here the different tests, non-parametric tests are applied here, Persian chi-square, likelihood ratio, and linear by linear association. So you can see here in all cases the p-value is greater than 0.05. It means, and we have also measured the symmetry. These are symmetric in shape. You can see here as well. So here you can we can conclude that the education is independent of the gender. It means education is not gender specific. It is independent of the gender. So male also study in all 4 classes and female as well. So this education is not gender specific. Gender doesn't depend on the education, or education doesn't depend on the gender. Both are independent, and thus education is not gender specific. So this way we can apply the chi-square test to test the independence of the attributes under consideration. So I think this was all about today's discussion.